Welcome. Today we'll have a very interesting talk. So I'd like to welcome all the people here. It's a very large audience and all the viewers at home. We are going to hear a talk today, and it's about using cell phones to track moving objects. And it's given to us by Professor Alex Bayan. He's in the Civil Engineering Department. He's in our systems group, which is attempt to bring in people from all aspects of science and engineering to work on civil problems. Very often we have the most interesting problems, the most societally important problems, but traditionally not the most modern techniques. So we're trying to bring everybody into solving our problems. Alex is a representative of the Intelligent Infrastructure Thrust in Citrus. I'm Steve Glazer. I'm nominally responsible for the Intelligent Infrastructure Thrust. And think broadly of intelligent infrastructure. It isn't just measuring bridges. It isn't just measuring cars, even though these are nice applications. Alex's background is in aeronautical engineering at Stanford, even though I like to think of him more as an applied mathematician. And while we have a very focused topic today, what Alex is working on is the Lagrangian PDEs, so he can solve very complicated systems where all the actors are moving, they're all moving in different directions, not necessarily independently of each other, and all the values are constantly changing. So how can we model systems like that? And it's an important problem. Why do we have an example with cars? Because basically the cars are going every which way, the velocity is changing. So with too much of an introduction, I'll give you Alex.
Thank you, Steve. Thank you all for coming. I'm very happy and honored to be part of this seminar series at Citrus. The title of my talk today will be Mobility Tracking in Large-Scale Infrastructure Systems. And in fact, I will have two applications. Even though the title slide only shows highways, I'm going to switch back and forth between road traffic and water. So without further ado, this is the outline of the talk. As Steve mentioned in the introduction, the goal of this research is really to track mobility and use large-scale system models to incorporate Lagrangian measurements, which are measurements which travel with trajectories of objects, into these models. There's two main motivation applications which I want to talk about today. The first one is the one that you just saw in the picture, which is the highway traffic monitoring application, so mostly transportation networks. And the second one is a flow reconstruction for shallow water flows, which bears a lot of similarities with the highway traffic flow in that it evolves on a network and it can be more or less modeled with one-dimensional partial differential equations. I'm going to then move into the techniques that we apply, and I'm going to stay voluntarily at a relatively high level to have some degree of commonality between the two topics and applications to illustrate how we can incorporate mobile measurements into flow models. And finally, talk about experiments that we have done both for the highway and the water. So this will, if some of you have been part of the February 8th Mobile Century experiment, you might have seen this already, partially. It's a big experiment we did on the California highways to demonstrate the technology, and then also talk about another experiment involving a submarine and a couple drifters evolving in the Sacramento Delta. So really, at the heart of this talk is the need of devising algorithms to incorporate mobility into models. Now that we're at the age of mobile agents where we can send robots everywhere, we have a relatively good control over where we can send agents, or at least we have some technology to be able to have agents monitor things autonomously. But one of the fundamental questions is how to use that information and how to incorporate that information into some physical knowledge of the system of interest, may it be traffic, may it be water, may it be the atmosphere, or other systems. So in the case of highway traffic, the main question is how to go beyond the age of static sensing A lot of us here live in California and very familiar with traffic jams and congestion that is very common in our urban freeways. Most of us have probably seen this San Francisco 25-minute sign on the highway. And in fact, you probably know that all this sensing and all the information which is on these displays. Okay, so that's. My computer might crash in the middle of a presentation, so I want to apologize in advance if that happens. So most of the information that is used in the systems comes from static sensors. This information is available for users onto websites like this one, if you've used it in the Bay, 511.org, traffic.com. If you're in the business of planning and you're more interested in long-term statistics, then PAMS, which was developed originally at Berkeley, is a good database for this. And the commonality of all the data that comes into these websites or services is that they're collected from sensors, which for some of them have been developed for and deployed for up to 20 or 30 years, like the loop detectors we have here on California highways, or a more modern version, which is now wireless and also was a Berkeley product in the group of developed by the group of Praveen Varaya. And more recent technology also used for specific locations. Camera data is fairly common and provides high accuracy traffic data. And in specific places like in the Bay Area or on the East Coast with EasyPass, you have these RFID transponders that travel on board cars, which check in at several locations on the highway beyond the toll and therefore provide traveler information. I guess the commonality of this technology is that either it's extremely expensive to deploy because you have to embed the loops in the pavement or the sensors in the pavement, or it's very specific. And in fact, if you live in Nebraska, there is no EasyPass, there is no fast track, so this thing just doesn't exist there. And that gives the cell phone an unprecedented opportunity to provide an alternate source of data. And if you take this cell phone, the N95, which is the one we've been using for our experiments, and you look at this suite of all sensors which is in there beyond the GPS, it's amazing how much you can do with it. This one now has even an accelerometer. It's actually a tilt meter. And so given the high penetration rate of these phones, which for now are still high-end phones, but in about 2 years will be really the $1 phone you get on your plans, suddenly we find ourselves with a totally new source of data, which is GPS data for travelers on the highway. Now, as Steve mentioned before, we're in a civil engineering department, so in a sense it is legal for us to rely on a communication infrastructure that is developed by cell phone operators. We're not in the military business, so in a sense we have the luxury of using such an infrastructure, which for civil engineering applications, of course, is a very good thing, because that infrastructure, especially in a country like the United States, is all over the place. And therefore, in fact, the cell phone network will be the same network we also use for the water application. So just to illustrate what you can get with today's cell phone, this is just a track of a student of mine taking a ride on I-80 down in Emeryville. So basically, Nokia gave us these phones a couple months ago. So the first thing we did is, well, let's see if this is a good thing to track traffic on the highway, and can we convince the California Department of Transportation that this would be a good sensor to do that job. And what I'm trying to convey here is that when you measure speeds of vehicles with a phone, you get readings which are fairly accurate, not only in terms of magnitude of the velocity computed by the GPS on board the phone, but also in terms of location. And that's the main difference with triangulation or trilateration. In fact, if you download Google Maps on any of these phones from Nokia, you can, and even if you don't turn the GPS on, you can find your position using trilateration, and usually the accuracy is about 1 mile or 1 kilometer, which is obviously disastrous if you're trying to compute speed, or even in terms of position, it would not be very good thing in terms of figuring out occupancies on the highway. So clearly you can see from this relatively graphic and accurate data, if you compare this to what has been available for the last 10 or 15 years with trilateration, we suddenly have a leap forward in terms of accuracy. And this is in part why, if you look in the literature, you will find dozens, if not hundreds, of studies which have been done with trial iteration. And the roadblock that they all hit is this problem of accuracy, which now finally is removed. And just to illustrate this, this is the speed for this guy taking this ride back and forth on the highway. This would be the speed history on the GPS and in the speedometer of the car. And every time I show this movie around, I always say that I really have more faith in the phone than in the speedometer of the car. At the core of this technology and set of algorithms that we are developing, there is really a novel source of data, which is illustrated by this movie here. This was one of our preliminary tests. We were running 20 cars back and forth on the highway, and which is really providing us with a source of data that we can now use as our main data feed for what we're doing. Obviously, this is extremely privacy intruding. You can see exactly what people are doing. You can see which off-ramps they're exiting. You can see the speed at which they're going. You can see a lot about their lives. In fact, you can even track people all the way home. So the main challenge of the study will be to figure out a way to sample this data in a way that is accurate enough for the model reconstruction, but at the same time preserves privacy of the users. And so what we did in collaboration with Nokia over the last 6 months is develop a system that gathers data from the phones, send it to an ID proxy server, which strips out the ID of the user so that it's really anonymous data, sends it to what is called a VTL server, which is a form of gathering server which aggregates data at specific locations on the highway, and sends it to a model server, which is another server on which we develop inverse modeling algorithms to compute and estimate the state of the highway, which can be then used for visualization. This architecture that I'm showing here is is I guess a commonality of any mobile or mobility tracking applications. In fact, the ones we're developing for the water application is almost identical. The specific feature which Nokia came up with in order to preserve privacy for this type of work is the concept of virtual trip line, which is a form of a geographic marker which should be considered as a trigger. So every time a car is driving through these virtual lines, which are defined by GPS coordinates, something happens. So what happens today is the car will just send a speed and position update. It's what the current system is doing because at least when this type of information is shared, privacy experts have assessed that it is not privacy intruding, and in other words, it will preserve participants' privacy. As far as we're concerned in transportation engineering, this is just a trigger, i.e. what we would like to do is use this as a trigger to maybe track the car for 2 minutes and get extra information beyond the just location and speed of the car when it went through the VTL. And the reason why we would like to do this is because if you have additional knowledge, which might not be too privacy intruding, following someone for 30 seconds is maybe not that privacy intruding, then you can gain a lot of additional information about the state of the system, maybe at no additional privacy cost. To illustrate how the VTL data is gathered, you can see these scattered points here popping out at specific location. This would be an illustration, this is true data, this would be an illustration of VTL updates close to some on-ramps and off-ramps on the highway. And you can visually at least assess that from that data, it's not clear how many cars went through this, how fast they were going you can get from the measurements, but the ID of the car is removed, so you don't know who it was. And therefore, at least convince yourself that it is a privacy preserving system which provides some guarantees to the users. In fact, the people working on this are at Rutgers University and have specifically addressed this problem of privacy. So the key questions that arise from the design of a system like this is, first, you would like to have some accuracy in your predictions. At the same time, you would like to preserve privacy, so you want to find a good meeting point at which both specifications are met. And obviously, when this evolves into a product, probably in about a year or year and a half, then a lot of other considerations will come in the pictures. GPS costs a lot of energy, so you cannot afford to track people for too long. In fact, on this N95 phone, if I turn my GPS on, I think if I use it to its fullest extent, I will probably empty my battery within 3 or 4 hours. So clearly not an option as a permanent basis. So efficient sampling strategies need to be developed in order to use this efficiently. Bandwidth obviously is also an issue, especially in congested areas, so one needs to come up with good strategies to not kill the bandwidth of the system if one wants to work with this. Once this is solved and once this has been implemented, a lot of applications become possible, and the main application, the key thing that we will go for first will be really the computation of travel time, and from there itineraries and route advisories. One thing that we cannot get from cell phones today that one could get from PEMS is the notion of flows and occupancy. Obviously, only a sub-proportion of people carry these, and even in 2 or 3 years, when that proportion becomes higher and higher, this is only a partial part of the fleet of cars traveling on the highways. So there is still a lot of work to be done to try to figure out a way to go from speeds to densities and flows, which is for now an open problem. There's a lot of hand-waving arguments that have been developed and heuristics, but there is no good theory for it. So the second example that I would like to use as a motivation for this talk is the problem of flow reconstruction in the Sacramento Delta. For those of us who live in California, we're somewhat familiar with the geography and topography of the bay. And at the core of the bay is the Sacramento-San Joaquin Delta, which is a very interesting network of water channels, which exhibit a lot of interesting features from a hydrodynamic perspective, which have a lot of very significant environmental impacts. So San Francisco on that picture would be about here. And the delta is tidally forced by the tides, which creates salt intrusion in the network this way. The pumps which pump water for Southern California are here. And, well, it turns out that the clean water comes from here. The water coming from the San Joaquin River is relatively polluted and therefore not great for human consumption. So the grand vision of the Department of Water Resources would be to have these two streams of water cross without mixing and without being polluted by the salt. Obviously, this is a big challenge, but this is not necessarily something which is out of reach, in that there is 1,000 kilometers of water channels here. There's a bunch of gates and dams that can be operated on tidal timescale. So if one finds the right model to characterize the timescales at which the mixing occurs, maybe there is some hope to have this happen without having a too costly infrastructure development. And again, going back to the introduction of Steve, I think the infrastructure aspect of both projects is clear here, because what we're trying to do and what we will kind of try to derive here is a set of floating sensors that will help build infrastructure and eventually be integrated in that infrastructure to help with the monitoring of the delta. Why is that an important problem? Well, there's many reasons. There's contaminant propagation. There's heavy rains, which provide a lot of sediment intrusions. And we have a lot of earthquakes. And as we've seen in New Orleans, the breach of a levee can be disastrous. And it's not only in Louisiana, but here. If you look in 2004, there was a breach of a levee at the Jones Tract, resulting into a big flood, which is here. Very serious accident here. This is now permanently flooded. It turned out it became a water park. However, when that happened, they had to stop the pumps for 3 days, and stopping the pumps in the south of the Delta costs $1 million a day. If you could deploy a floating sensor network real fast, you could assess the progression of the salt, you could assess the recalibration needed for the hydrodynamic models, and based on this, operate the system and understand the system much more efficiently. And that's just one of the many illustrations why this technology, this floating sensor network technology, would be helpful. Now currently, if you go in the delta, most of the sensing that is done is static. So you have about 50 points which have these very static and massive sensor stations developed by the Department of Water Resources and U.S. Geological Survey. And I mean, I don't think anybody needs to take a too advanced signal processing class to understand that 50 sampling points for a network of 1,000 kilometers of water channel is really undersampled. And so clearly, if one wants some good understanding of the precise hydrodynamics at these junctions and overall a good picture of the system, additional sensing is required. And exactly like in the highway case, developing a floating sensor and throwing it in the water is much more cheaper. It's much cheaper and also much more dynamic than developing these big and massive stations, which are good for long-term statistics, but might not exactly meet some operational needs, especially in the presence of unanticipated events. So the vision here is very similar to the one I showed for the cell phone, in that for the highway, in that what we're trying to do is to develop a set of floating sensors, which are all linked wirelessly, also through a GSM module, through a base station on the deployment site, or now virtually here at Berkeley, and in which we can use power computing to do inverse model and predict the current in real time. In fact, now we're even moving in the heterogeneous agent business. We have a submarine that we can use every year from another university in Portugal that will progressively become interactive with the sensors here. So the vision, again, is you have these sensors, and they're linked wirelessly. They're all made at Berkeley. Right now we have 20 of them, so they're manufactured by my graduate students and some of my PhD students. And you can interact with them through the cell phone network. Our plan is for next year to deploy 100 of them. In fact, Nokia has donated 195 phones, which we put on the highway, so we might just as well put it in the water. Makes them a little bit nervous, but we'll make sure that none of them sinks. I mean, it's more dangerous for a phone to be floating than to be in a car. So I guess the long-term vision is we might as well, so there's really two things here. One of the things is there's operational deployments, in a specific case to monitor some specific features of a hydrodynamic junction at a given time if we're interested. But there's also a longer vision in which we might really help the Department of Water Resources and U.S. Geological Survey to instrument the delta. So really having a link between these things, which are dynamics and float, and the more static and permanent sensor stations, which we can access and interact with through the internet. Everything can be downloaded in real time. And for specific deployments, also submarines that we can play with once in a while. So these two applications share the same feature, the same mathematical feature, in that in both cases you have mobile agents, which you can't really control. If you think about floaters and 6 feet a second current in the delta, there's nothing you could really do. Some of them are motorized, but there's nothing you can do. You're going to burn your battery real fast. And if you're a cell phone traveling on board a car, well, you just go wherever the person is going. So the commonality of these two things is that there's very little actuation. You can only sense where you're going. You don't really know why you're going there. And the main challenge is, given these constraints in motion, how to reconstruct a good estimation of the system, of the state of the system. And this is really the fundamental difference with a lot of the literature that has been published on multiple agents assumes that you can control your motion and that you can send your fleet wherever you want. Well, in a sense, that's almost the opposite. There is almost nothing you can do here except maybe readjust your position if you're in the water. And okay, if you're the submarine, you have a relatively good flexibility, but that's, of course, we're not going to deploy a fleet of submarines. If we ever have 5 submarines operating at the same time, then we'll be a very happy university research group. So the real mathematical challenge here is, given this constraint motion, which is really forced by the infrastructure, how to reconstruct the state of the system based on the distributed parameter systems model. So for this, we need to use mathematical models which are distributed in nature, and I think that's clear from both applications. This 1,000 kilometers of water channels, or these network of highways. And so in the specific case of the highway, first-order models, which are first-order hyperbolic conservation models, are very good approximation of flow and traffic. Okay, so you have density of cars, which is modeled by a function which is space and time dependent, and its evolution is characterized by the speedy here, which relates its rate of change in time to the divergence of the flux, which is characterizing the inflows into control volumes in the system. Skipping the mathematical details, you have to go a little bit beyond imposing boundary conditions in the strong sense. You have to impose this in the weak sense, and I'm going to show this in a minute. And this Q function here, which appears in the divergence operator, is also something that can be understood fairly intuitively from data. So this flux function here relates the flux of cars to the density of cars. And if we have all been in a congestion sometime in our life, we know that the flux on highway is more or less proportional to the number of people until congestion happens, at what time it starts to decrease. And when it reaches zero, it means you're really stuck on the highway. So grouping all this together, you can write this PDE, you can write some initial conditions, you can write some weak boundary conditions which are required for this to be mathematically valid. You can even generalize this to a network, and that provides a good mathematical model of the evolution of traffic density on the highway. So if you have ever looked at 511 traffic, .com, INRIX, or any other kind of website, usually there's a color code, and the level of the color, if you look carefully for specific data, is in fact proportional to the density. So black means high density, green means almost zero density or free flow. Now, in the shallow water equation case, the equations are a little bit more complicated. It's a three-dimensional system in which you have three state variables. H is the height of the water, U is the velocity in the x direction, if you choose any coordinate system, and V in the orthogonal direction. The point is, exactly like in the highway case, even though this is one-dimensional and fairly straightly easy to understand because there's a form of a conservation of a fluid in a pipe, well, it's a bit more complicated, but it has very similar features. Depending on the regime in which you're operating, this is a hyperbolic system. Unlike in the highway case, it does not have shocks. Because in the area in which we are, the flows are very subcritical. It's not like there's some places in Vietnam where there's bores and you really have shock waves that happen. In a sense, these equations are they're much nicer to deal with because they don't exhibit a lot of the features that we have in the highway case where we really see shock waves propagating back and forth in the system. So both for the highway and for the water case, the point is that in both cases, you have static measurements. Okay, so I'm just illustrating this here for the highway. Static measurements by static sensors. And then you have, in some cases, mobile measurements, which are measurements brought by our mobile sensors. And what we would like to do is to create a mathematical framework which enables to incorporate both of these measurements into a single model. So there's a lot of different inversion techniques that can be used for this. And I will not have time to go through all of the ones we have used, but all of them more or less work the same way. You have an underlying model, in our case a PDE, which is discretized in the form of a ODE, or of a discrete nonlinear dynamical system. And the measurements, the Lagrangian measurements, the mobile measurements that you incorporate into the system are put into an estimator, which provides a best estimate of the state in some sense. So for example, if you're using Kalman filtering, you're going to use a least square best estimate. If you're using other methods like nudging, you don't have a guarantee on the type of the estimate you get. But in all the techniques that are used, if they're adjoint based, if they're Kalman filtering based, if they're nudging based, quadratic programming based, you're providing an estimator, which is a copy of your state, which is as close as possible to your state. So I'm going to illustrate this methodology for both systems of interest. To give you an idea of the way you test whether an estimation algorithm is good or not, the standard procedure which is used and which is really due to oceanography is called twin experiments. So you come up with an algorithm which estimates or provide an estimate of your state, and then you want to assess how good that estimate is. So for this, you will first run a simulation, which you will consider as the ground truth. So in the highway case, Paramix, which is a simulation software, is a very good way of doing this. So Paramix is a software that simulates the state of the highway, including all the cars everywhere. And from this very highly calibrated traffic micro-simulation, you get what you consider the ground truth, okay? And you know everything about this because it's a simulation that you entirely have done yourself. So you know everything about the system. Then you put it in your model. So CTMV here stands for my model. And using any kind of algorithms that will be relevant for the model, so in the highway case, it's an ensemble Kalman filtering algorithm, you provide an estimate of the state of the system, which you can compare to your ground truth. A very simple procedure that is used both in oceanography and also in highway traffic flow engineering. Okay, and so when we do this with Paramex data, which is the main source of microsimulation data for highway traffic, what we can do is we can compare ground truth to ensemble Kalman filtering velocity. And in that case, what we're looking at here is the post mile, that's the distance on the highway, as well as the time. And black indicates low speeds, okay? So I'm just showing this visually. Obviously, we can run statistical estimates of how good we're doing. But the first step before even trying it on the highway is to just try it in a model where we exactly know the state of all the system so that we can really compare the estimate to something we fully know. And based on this, you can run a lot of studies which, for example, can assess the influence of the penetration rate of the sensors on your system. And the idea is that, well, with a higher penetration rate of vehicles on the highway, so let's say 5%, 10%, or 15% of the vehicles equipped, you should be able to get a better precision, i.e. less error in your estimate, which is displayed by these curves here. Okay? So this is kind of the preliminary stage that is required to make these algorithms work. Now, there is a reason why Lagrangian sensing provides good results and really improves the estimates you could get if you only had Eulerian sensing. And these are fairly easy to see if you look at data. In fact, if you look at this diagram here where you have a Eulerian sensor here, Eulerian sensor there, and assume you know some boundary condition here, some initial condition here, if you could follow a car along a trajectory, and if you had the knowledge of the action of the car here, where the car brakes, without this being able to predict in the model, because in fact no model predicts whether you're going to brake in the middle of the highway or not, because that's due to an external disturbance. If you're braking here, it's probably because either you're scared or you saw a police car or someone called you on your phone or something happened, but you cannot predict this mathematically. What you can predict mathematically is the effect it will have on trajectories behind, because that's just a single propagation of a shock wave. So just the knowledge of this trajectory here gives you a lot of extra information which clearly can augment what you can get from static sensors. And to illustrate this, the color level here indicates the level of error that is due to the prediction of the model. And so in that case, if you just play with one sensor here, you can see black means low error. So you have relatively small error close to the sensors. Imagine now you add another sensor here. And this is for real data. This is another data set that we use, which is NGSIM data, where we know the whole truth because we have video data for all the cars. So if you add another sensor here, then again, you reduce your error locally, but in the middle of that stretch, you still have a high level of error. And then here's some studies we can run with these models, and this one is in fact obtained by solving a Hamilton-Jacobi equation, which represents the evolution of the cumulative counts on the highway. Here are the types of added value that you can get by plugging in additional GPS tracks somewhere in the middle of that stretch of highway. And I'm illustrating this, in fact, visually, but this is using an algorithm which was just accepted to the SIAM Journal on Control and Optimization. And the key here is to define the mathematical solution, which at the same time is compatible with the boundary conditions and with the internal conditions, which is something not that common when you look at the literature on PDEs. And the good thing about this result is that this mathematical framework we have developed enables you to pretty much incorporate anything you want that is internal, in particular tracking people for 30 seconds, which I think would be a good option to do and not too privacy intruding, and see how locally that decreases the error. Again, black here is a good thing because it means the local error of the predictions is small. Now, in the water case, the very similar concept of twin experiment is used very frequently as well. So what you can see in this movie is a simulation of releases of drifters. And the twin experiment in that context consists in doing exactly the same as we did for the highway. So what you do is you do a forward simulation. In that case, we use MIKES, which is one of the most acknowledged 2D shallow water solver that is available commercially. And MIKES has a very nice feature is that you can actually simulate Lagrangian trajectories of drifters inside the software. And that gives you a ground truth. Not only do you know the trajectories, but you also know the velocity field everywhere. And then you move to a second model to do the inversion. So we use another software, and that's Telemac, which is also a very famous software to solve 2D shallow water equations. And on Telemac, we can use several algorithms that are good to do this inverse modeling. In particular, ensemble-Kalman filtering can be directly done using Monte Carlo runs of Telemac. And then also using degraded models, quadratic programming approaches are a good way to inverse the system. So again, using this concept of twin experiment, one can assess how well the algorithm do. And so most of our mathematical contributions in that field have been to find good numerical algorithms to A, discretize the PDE in the way that the inversion is feasible, and B, to do it in a computationally efficient way. For example, if one uses quadratic programming on linearized version of the shallow water equations, then that can be solved very quickly. And you don't even need a very large software to do this. I'm going to skip this, but you can assess the accuracy of the predictions using these twin experiments. So in the last couple of minutes of the talk, I want to talk about the two experiments that we have run to show that this things work in practice. So in the case of the highway, in February, we deployed 100 cars, and we had 165 drivers drive these cars in loops, in 10-mile loops around Fremont, the Fremont area, which was a way to in a sense, get a glimpse at what will happen in about 2 years when you have about 5 or 10% of cars traveling on board highways in California equipped with these phones. So this is a preliminary experiment we ran in November with 20 cars. And the setup that we used on February 8th was very similar. So it's basically a bunch of drivers driving a car with this N95 phone on the dashboard, and then going to this deployment area in Fremont, and then looping back and forth for a couple of hours. And again, here the idea is that by having these loops going back and forth, in a sense, you're recreating what will happen in about 18 months or 2 years, in which now you have a high enough penetration rate of cars on the highway to reconstruct traffic jams. So basically, the patterns followed by the drivers are just back and forth loops over and over. And in all these plots, you're going to see the color level indicates the speed. So you can see this bottleneck created here that will persist, in fact, throughout the experiment. This is a recurring feature of that stretch of highway that we knew ahead of time, and which was one of the reasons why we selected that place to run the experiment. So the server that I showed was first tested on this 20-car experiment. And then on February 8th, then we replicated the experiment with 100 cars. So now to create more complex travel features, we had several loops. So you had in the morning long loops, because there's a free flow condition, and in the afternoon you had short loops because the flow was congested, so you wanted to have shorter loops. And then these 100 drivers drove back and forth for about 8 or 9 hours. So we actually paid them $250 to do this and give them a free Bluetooth headset, because you could give students a little bit of compensation to do this. But this created an incredible and unprecedented database that is, of course, very good for us to test the accuracy of our algorithms. Additionally, we had camera crews on the bridges that were recording traffic in the form of video data that you can see here. And here the goal is not to film the whole stretch of highway, but to do license plate re-identification. So if you can do license plate re-identification like this, and you can track a license plate from here to here to here, then you know the exact travel time, and that's a form of ground truth. Here, clearly, 10 hours of traffic at a 2,000 vehicle per lane per hour rate, there's no way we could ever, even with a helicopter, film everything. So there's no way to have the full ground truth, but we can at least get some idea of travel time by just re-identifying license plates for that duration of the experiment from the bridges. I'm just going to show a couple pictures of the experiment and then some results. So this gives you an idea of the setup we had. We had a bunch of cars lined up on the parking lot, and then students resting in a tent and taking turns to drive cars. We had a LCD screen display that were broadcasting our inverse modeling algorithm results in real time. So this color code is pretty similar to the one you see on the web when you go to 511 or traffic.com, and broadcasting traffic jams that we could identify based on these Lagrangian measurements. There are some team members, Caltrans operators helping us to set up the experiment, lots of logistics involved, as you can see. Some officials came. In fact, these are some of the camera teams on the bridge. This is the CTO of Nokia who came in for the day. For the experiment, we had a press conference. In fact, we had a lot of media coverage. In fact, there is a show running in about 1 hour and 15 minutes on Cable 5 or ABC, I don't know, so today, on this experiment. And so one of the striking features that happened during the experiment is at 10:30 there was this big traffic jam that created here, when in appearance, when people were looking out 2 miles south of the traffic jam, traffic was flowing really freely. So that raised a lot of questions. What you see here is someone phoning to, I think, the command center of either traffic.com or a Caltrans center to get a confirmation of this very surprising thing. And in fact, what had happened at that very moment is there was a 5-car pileup accident, and we ended up detecting it almost as fast, if not even faster, than some of the websites that were running the estimation algorithms for themselves based on static sensing. And so for us, as soon as we got confirmation of the accident, it was a really good thing, because it really validated not only the accuracy of our system, but also its usefulness. So in fact, if you had looked at 511.org on that day, this is what you would have seen. So kind of bottleneck here. And this is what we had on our screen. We are not using the same color code and not the same interface, but we captured that really precisely. And not only this, but we also had some good speed measurements. This is what happened when the traffic incident got even worse. And last result, just to show the potential of this data, if you've ever used the PEMS database, this is what you would have seen on that day. So this is the time of the day, and this is the post-mile. And this blue thing is the congestion due to the incident. This is a very small portion of the GPS data for that very same day. And what is striking, and we are now running statistical tests on this, and what is striking here is the similarity of these two plots, which really gives us hope that what we're doing not only is an extremely rich data source, but also the algorithms that we are implementing on this data will really provide a lot of value to the system. So I have about 3 more minutes to tell you about the other experiment that we run in the water. Just to give you a glimpse, this is a subset of the vehicles on February 8th. We only plot 25, because when you start to plot 100 vehicles, it really becomes totally incomprehensible. But that gives you an idea of the dynamics of the vehicles on the day of the experiment. And you can see when they go north, a lot of them getting stuck in these kind of slow-moving areas here. I'm just going to move real quickly to I guess there's really a parallel between the highway and the water. And so what we did for the highway, we're also doing for the water, i.e. we're reconstructing flows in the delta. This would be an example of flow reconstructed from these inverse models. From that, we can gain a lot of information solving Hamilton-Jacobi equations about very important quantities if you want to have autonomous agents evolving in the delta, in particular survival time. So if I'm a drifter, how long is it going to take me before I totally fly out of this domain? I can just show you very briefly a deployment. One of our very first deployments, you can see these drifters going down here. It was one of the first tests we did. And this is kind of our boat grabbing the drifters before they go away and then pulling them back up. So this is still at an early phase, I mean, obviously in comparison to what we do with the highways. But the currents we are able to reconstruct are very helpful. So for example, now that we're in the business of navigating submarines, we can solve Hamilton-Jacobi equations to compute minimum time. And if you're a submarine and you try to go to this place in minimum time, these would be the isochrones you have to go through, which are basically the lines of equal time to reach, which we can use to compute optimal control and optimal trajectories. And in fact, a couple months ago, we did our first submarine deployment. In fact, this submarine was given to us for a couple weeks from a university in Portugal. and you can see the trajectories resulting from the experiment. So I want to show one last movie, which is kind of the trajectory of the submarine, and I think this will also illustrate, so this, obviously this is happening underwater, so we don't have a movie of the submarine, but this is a reconstruction of the measured position from acoustic ping and sonar of the submarine throughout the experiment, and this is the submarine pretty much following an optimal trajectory that has been computed by solving the Hamilton-Jacobi equation, for which the velocity field is obtained from our inverse models. So I guess I want to end up with this for this particular example to illustrate the fact that in both cases we're dealing with mobile agents. When we have the luxury of free motion, like in the submarine case, that can really pretty much follow optimal path as we wish, we're in good shape. But most of the time, we really don't have that luxury. And well, when that is the case, then the best we can hope for in terms of reconstruction of flow fields, be it water or highway, is really to have inverse modeling algorithms which are as accurate as possible in terms of the data assimilation that you can use using mobile sensing. So I will stop here, and I think we maybe have a couple minutes for a couple of questions.
Couple questions. So first, thank you so much for a great talk. If you have any questions here, you can take them quickly. All right.
So probably two questions. One, a very quick one for the last thing you showed with the submarine. Did you sort of had a little race between a submarine that went in a straight line and the submarine that followed the trajectory to actually prove that it really was the shortest time?
No. Okay. So first, it's not following a straight line. The curve it's following, it's a minimum time trajectory that is obtained in using optimal control. So the goal of that movie, or the goal of that experiment, was to show that we're able to use a Hamilton-Jacobi algorithm to construct a minimum time trajectory and to follow it in a non-uniform, non-static current.
The other question I had is there's apparently a static sensor system out there, and I understand that it's working apparently quite well. And what you're saying is that your GPS-based system would be cheaper and would be deployable more easily in areas where there isn't static sensors.
Yes. So the
but
system,
what's the advantage for areas which already have the static sensors?
Exactly. So the static sensors are working very well, but obviously there's only 50 of them, so it's not enough to sample what happens at junctions. And so already there are places where you don't have good measurements if you wanted some local things. So for there, you really need to deploy your own sensors. And then additionally to this, these sensors give really good result at large scales because they only measure flow and stage. But if you want to characterize smaller space and time scale features of the hydrodynamics, then you really need local measurements. And there's many reasons why you want to do this, and I just can give one of them. If you're interested in salmon migration, salmons are extremely sensitive to the currents that you cannot get from these static sensors. So it's not that one is better than the other one, it's just that these new sensors, in a sense, enable a lot of new applications that we can't just do with static sensors.
Great. Do we have any other questions? Here we go.
So for the traffic sensing, if this were to become an actual program, how would it be implemented? Would it be like something that you can voluntarily sign your phone up to, or?
Right. In fact, we are now moving in the millennium phase. This was the century phase where we were 100 phones. Now we're moving into the millennium phase where this is evolving into a product. And so the way it's going to work, this is already in negotiation between Nokia and some operators, is in the first phase of the deployment of the product, people are going to sign in for a service. Maybe we're going to give them some rebate. Maybe we're going to offer them a free phone to start with in exchange of their data. In the future, so this is in the deployment phase because we need to get enough cars out there, and so we are shooting for maybe a couple thousands within 1 year. And then once the penetration rate becomes locally enough, then we hope that these things will perpetuate itself. And so this is an interesting case where the Century experiment was an experiment. We were briefing drivers, we were collecting data in our own system, so it was really an experiment. This next phase is really a pilot and potentially moving into a product. Yeah.
And how are you going to do this, I mean, like most people, you know, we're going to be in traffic, you know, around 9 o'clock and around 5 o'clock. But, you know, you're going to have, your system going to work very well during that time. But all the times in between, you're not going to have a lot of cell phones out there.
Okay, and so in fact we want to, so it's a really good question, because the first thing we want to do is to exactly take advantage of this. We want to select people who commute at 9 and 5 to get, at least locally in time, a high enough penetration rate, to demonstrate that this thing works even without briefing the drivers, even without knowing when and exactly where they're going to go and everything. I think in terms of showing that the system works, it will be enough. And then I think there will be one transition phase between that stage, where it's still kind of prototypical, 10,000 people, and when it goes national. And that phase, I think, can fairly well be covered by a hybrid of what's already there and owned by Traffic.com, which itself belongs to Navtech, which belongs to Nokia. Or, I mean, the merger is not finished, but it's in the process. And that will be a good transition stage before things go really national. So obviously there are some non-trivial things solved, but I think that moving a little